Welcome back to ECE 442-542. Homework number 5 is due on Monday, the 3rd, as is deliverable number 1. If you're in ECE 542, your deliverable for your project is due, deliverable 1, and that's not phase 1. Deliverable number 1 is not the same as phase 1. So the project is organized in phase 1, phase 2, phase 3. That's just to give you a way to process the project, but deliverable number 1 is simply to tell me what you're doing or planning to do for your project. Make sure you're clear on that distinction. I have created one supplemental lecture, and I hope to create some more. And that one right now is competing performance specifications, which is consistent with homework assignment number 5. You may have given 3 different performance specifications. They may not immediately be simultaneously achieved. And you may have to adjust one or more of those performance specifications in order to get all 3 to be satisfied. And that's covered in that competing performance specification material. Exam number 3 material is available on D2L, and we will have a review session for exam number 3 a week from Monday on the 10th of April. The 10th of April is a Monday. It's not a Wednesday. Our exam is on Wednesday the 12th. Exam number 3 is April 12th. Today what I have to do is, one, I want to talk about hints or helps for homework number 5. Some of you have already started homework 5, but hopefully these hints and helps will speed up the process of working through homework number 5. We'll then try to finish up the justifications for the 4 restrictions due to or that exist on the Ragazzini design approach. 2 of those restrictions you want to always be using, and that is never, never, never cancel unstable zeros or zeros outside the unit circle with your controller. Never, never, never cancel unstable poles. Those are poles outside the unit circle with your controller. Now in the Ragazzini, we're canceling those in the control design formula, but that's so that the controller itself doesn't end up canceling those poles and zeros. So there is a distinction between what do you mean you're canceling or not canceling. But restriction 2 and 3 refer you to or say never cancel with your controller unstable poles or unstable zeros. So don't be canceling things outside the unit circle. You can position poles and zeros outside the unit circle. That's allowed. You can drop things outside the unit circle. And last time we saw that 2 wrongs can make a right. We started with an unstable plant. We put in or designed an unstable controller, and that combination in the closed-loop feedback provided us with a stable closed-loop system. So 2 wrongs in that sense can make a right if you consider a controller by itself wrong, but that's just meaning we're using that terminology to refer to that controller maybe having an unstable zero or an unstable pole. So we'll try to get through the justification of why we have the Ragazzini restrictions. We'll do an overview of PID, proportional integral derivative control, and then we'll start getting into proportional control, which I hope naturally leads us into limits on the gain K for stability. And that will naturally lead us into root loci and creating these properties for sketching a root locus associated with our poles and zeros in the Z-plane. That's where we are headed. Hints and helps for homework number 5. Problems 1 and 2. There are multiple parts, and that's to give you practice. But what you're wanting to do is you want to create this desired closed-loop transfer function, capital T sub C of Z. And in most of them, I think your numerator is just going to be KZ. probably. I may say force a 0 at the origin. That just means you have a value of z equal to 0 that causes the numerator to vanish. But your denominator now is you're trying to figure out what is alpha 0 and alpha 1. And that's going to depend on these performance specifications that we've talked about in the 3 previous lectures. How do you now determine where in the complex z-plane you locate your complex poles consistent with your performance specifications? And in some cases, you may have a lot of freedom. Maybe I give you a settling time specification. So settling time, what do you see with settling time? Geometric shape. Circle. So now if you have circles, and you only have circles, now what do? You're trying to find 2 points so that you can find an alpha 1 and an alpha 0. And all you know is the radius. Well, now it's up to you. Now it's your engineering judgment to figure out where do I locate these poles based on living somewhere on this radial or this circle. That could be a possibility. And a lot of times you get uncomfortable when it's not just one answer. Now there could be 100 different right answers to that same problem. So here with the settling time spec, that impacts the radius. You have this relationship between t-settle. If it was given in absolute units of time, it might be necessary to find it in terms of the number of sample periods, which we're calling n subset. And the 1% settling time says, oh, we raised that radius to higher and higher powers, and that's collapsing us down. And we want to know how much do we need to adjust, or how many times do we need to hit that radius before we get less than 0.01. And that's what the settling time really is doing for us. And we can solve that. And what we see is that if we want a shorter settling time or a faster response or a quicker system, then we need to be looking at closed loop poles not with a radius r1, but with a radius r sub 2, where r sub 2 is smaller in terms of a circle than r sub 1, and the faster rate says that r2 in magnitude is less than r sub 1. So when you hear settling time, you're seeing targets. You're seeing these concentric circles, and the smaller the circle, the faster the system responds. Problem number 3, and this may not be clear from the way it's worded, but I'm assuming that I think I give you an unstable system that has a pole at s equal 1. So I'm giving you a system 1 over s minus 1, but I want you to find the zero order hold equivalent of that g of s, which means you're now looking at this expression from an earlier part of the semester. Was that exam 2 or exam 1? It's exam 2, wasn't it? Where we were doing zero order holds. So now you apply that strategy to find your g of z. And once you've found g of z, you're ready to start designing, or you could have found your g of z from MATLAB. You could put in g of s, and g of s, if you use the right c to d function, and in this case, if you don't tell MATLAB what strategy to impose in going from continuous to discrete, that's the c to d function, it will assume that you want the zero order hold approximation. So if you don't say with a third argument in c to d what you're using to do this mapping from continuous to discrete, it defaults to the zero order hold equivalent. You give it the sample period 0.2, you tell it what g is, and g we've defined as a transfer function with a numerator of 1 and a denominator of s plus a minus 1. That gives us our s minus 1. We simply in MATLAB say c to d to get g sub d or gd, and we'll obtain then g of z equaling that. So that now you can see that we have, well, I guess I've already given you a hint. What do we know about g of z? What do we want to start thinking about when you look at g of z and you're trying to come up with a desired transfer function, capital T sub c of z? What's one of the first things, or what's restriction 1 telling you? You want to maintain the pole 0 excess or make it bigger, don't you, with T sub c of z? So you need to know what is my pole 0 excess with g of z to begin with. In this case, how many more poles do you have than zeros in this g of z? How many poles do you have? And maybe my writing is not very clean. I don't have a z up there. That's a 2. That's a 0.1052, not a 0.105z. I didn't put the line through the middle. So the numerator is only a constant. How many finite zeros do I have? 0. So I have a pole 0 excess of 1, and that's why I can say, oh, let's just try something simple. And in all of these, I think problems 3 and 4, I'm asking you to produce a deadbeat response. And what do I mean when I say a deadbeat response? Where do I want my poles? You want all of your poles at the origin. In this case, if we have a pole 0 excess, and if we want T sub c of z to be as simple as possible, if we don't want a lot of parameters to adjust, which in this case maybe we don't need a lot of parameters to adjust, we can have a pretty basic desired closed loop transfer function. Just say, oh, a gain over z. That does have a pole at the origin. Those are hints, hint, 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 for problem number 3. Problem number 4, you're given immediately the system, g of z, the system that you are trying to control. And now you start asking those questions that you need to ask before you start imposing or applying your strategy to design a controller based on Ragazzini's approach. Now, what's one of the things? Well, you need a causal controller. So now you want to know what's the pole 0 excess of g of z. How many poles do you have? Why isn't it 2? Oh, it's pole 0 excess, isn't it? Sorry, I'm just belaboring your answer. But yes, 1 is correct. It's 2 minus 1, which is 1. So we have a pole 0 excess of 1. I'm just making you question, and then you go, what? Just to make sure that you're locked in on your answer. Which implies what about your desired closed loop transfer function T sub c of z? It must have a pole 0 excess of at least. It has to be at least 1. And in this g of z, so now we want to move on. We now know what restriction 1 tells us. What about restrictions 2 and 3? Restrictions 2 and 3 deal with unstable zeros and unstable poles. We look at g of z and we say, do we have any unstable zeros or zeros outside the unit circle? There really aren't any consistent. Well, we talked about the phrasing of unstable zero before. I'm really just meaning zeros outside the unit circle when I say unstable zero. That's the definition of an unstable zero. It has nothing to do really with stability of your system. Do we have any unstable poles in our g of z? No, it's already in factored form, and they all have a magnitude less than 1. We have 1 at the origin and 1 at 0.9. So this next starred question, g of z has an unstable 0, and by restriction 2, that says we need to make sure that our desired closed-loop transfer function maintains or preserves that unstable zero factor. So that means we have to include in our desired closed-loop system a factor in the numerator of z minus 1.1. We have to do anything with restriction 3, which was concerned with 1 minus t sub c of z evaluated, and where is that evaluated at? That expression 1 minus t sub c of z, we needed it evaluated somewhere in restriction 3. Where do we evaluate it? Remember? At 1. 1's a common answer today, isn't it? One little something. Okay, I'll be quiet. Is it 1? Restriction 3 deals with what? Unstable poles. Did we have any unstable poles here? No, so we're hypothetically speaking. But if we had an unstable pole at 2, then we would evaluate 1 minus t sub c of z at that location z equal 2, so that that factor would have a 0 where we have the unstable pole. That's what we're using restriction 3 for. In problem 4, you don't have to worry about restriction 3, is what I'm saying. And now we can use k as a design parameter. How might you select k? Now, if we have a DC gain, now what's wild tonight? 1. So how do we use 1 in a DC gain? We can use it 2 different ways, right? We probably want our DC gain to equal 1, which means we want what kind of behavior for t sub c of z? We want it to equal 1 when? When z is equal to 1. That's why I'm saying 1 is wild. We used 1 twice there, didn't we? We were saying we want our DC gain of our desired closed-loop system to equal 1, but our DC gain is found by evaluating that at z equal to 1. So we were forcing that to equal 1, and there's the 2 different reasons for selecting z or a value of 1. And that's really then satisfying restriction 4, which may have not even been explicitly asked for. Now you're doing something extra. And as engineers, we're always building in additional objectives or goals. Not always, but in this case, it helps. It's not hurting. Is that called goal creep? What? Okay, I may just stop tonight's lecture. All right, let's talk now about restrictions of Ragazzini's design. So there's the help for homework number 5, which is due on Monday, April 3rd. Now let's talk about restrictions. And we already talked, I think, last time about this particular denominator piece, 1 minus t sub c of z being proper, and you might just plug in some particular transfer functions for t sub c of z, and then check to see if 1 minus t sub c of z is indeed proper, just to convince you that it is. Then, I have a lot of text here, but I know that you like to read as engineers. That's why you got into engineering. It's for your love of reading, probably. Most of you. I'm joking. But the pole 0 xs in g of z. So now think of g of z. We've put that now in the denominator. So if we had a pole 0 xs of 1 and we invert that, what's going to happen when we say 1 over something that has a pole 0 xs of 1? That pole in the denominator is going to pop up, and now we have in the first bracketed expression something that is improper. We have a higher power of z than we had or we have a higher power of z in the numerator than in the denominator. We don't want that. We want our c of z to be causal. And for that reason, and since the denominator 1 minus t sub c of z is proper, we're not changing the pole zero excess with that piece. So if we want to preserve or at least maintain causality, that's saying then that t sub c of z needs to possess at least the same pole zero excess as g of z, so that it accommodates the pole zero excess of our original system, g of z. And that we can see, hopefully, from this formula. If you don't see that, go home and play with some examples and see. I told you we're reading a novel tonight. I don't need you to write, necessarily, but I want you to read one of the R's. Okay, you can write in a minute. I'm going to slow down. See this little scroll bar, how low it is? We're almost done with this movie that I'm playing in front of you. So now, this restriction on the pole zero excess in t sub c of z hopefully makes sense. And like I said, we've already looked at what would happen if g of z had a pole zero excess of 1. What does that mean? If g of z has a pole zero excess of 1, we now have really one delay between if we put in an input to that system and look at the output. So we have a one-step delay between the input and the output. By forcing our desired closed-loop pole to have at least that same pole zero excess, we're assuring that we're not speeding up the behavior of our system. We're not creating something from nothing. We can't make our system go faster than it originally was in terms of the number of sample periods between the input and the output. And that's really what this restriction is giving us. It's allowing us to preserve this behavior or maintaining this one sample period delay if the pole zero excess is 1 between the input and the output. Question? Yes, so if we went the other direction and we made the, so the question was if we expand the number of, or increase our pole zero excess. So if we made t sub c of z have a pole zero excess of 2, now we have 2 delays between our input and our output. If it's a pole zero excess of 1, it has 1 sample period delay between the input and the output. If that was what our plant started with, what we're saying is we can't make that be 0 with t sub c of z. So we can't make our output become instantly seen when we apply an input. That would be a pole zero excess of 0. So we're trying not to make, with this restriction, we're avoiding that happening. So with a pole zero excess of the desired closed loop plant having the same pole zero excess as our original system, G of Z, then we're assuring that our controller is causal, meaning it's not using future errors to produce the present output or the present input to the system. So we're assuring causality by maintaining that pole zero excess. So that's restriction 1. Let's now look at deriving this expression in red that I've just been handing you up until this point. Where in the world did this come from? So let's now find the controller. The idea is we want to find this transfer function, capital C of Z, such that when we plug it into this closed loop system with a plant of G, that we end up with this desired closed loop transfer function, T sub C of Z. That's where this formula is really coming We want to see where that formula came from. And what we want to do now is find that controller, C of z, that realizes this desired closed-loop transfer function, capital T sub C of z, which is the transfer function between the reference input R and the output Y. If you are playing along, you can start taking notes. Just saying. So here's our controller. Here is our system or plant. We have our reference input R and our output Y. And I was talking last time about this cheer, and some of you felt left out, so I'm going to derive a different cheer tonight. And I realized when I was preparing for today's, I was saying the cheer, and it wasn't what we talked about before. It was wrong. You guys didn't correct me. But let's work on a different cheer today. And if we want, we could label this signal as an error signal, which is the difference if we were comparing where we want to go, which is R, to where we are at, which is the output Y. That's giving us an error signal B. I hope it's clear that if I wanted Y of Z, I could produce that from E of Z by just forming a product of the plant and the controller and injecting the error signal. Y of Z is now G of Z, C of Z, times E of Z. Y is GCE if I forget the argument. That should be clear. And we can, from this block diagram, identify E. That's the output of that summing junction, which should equal the inputs to that summing junction. And here I just have two inputs. I should just have two terms that comprise E of Z. And in that case, E of Z is just R of Z minus Y of Z. I hope that's clear. Now what we want to do is simply replace E in the first formula or equation with the E in the second equation, and then start solving. That's all we're doing. If we do that, now we can scroll past the block diagram. Y of Z is now G. Can I go ahead and forget the arguments? Okay. Is the classroom locked? It is now. Okay. I'll get both doors, don't worry. See how that really locks? You're not locked. They just spin. Kind of defeats the purpose. But we now have GC times E. And E is now R minus Y. This was just using our formula for E. Now let's combine all of our terms that contain Y's and R's. I'm going to now pull that GC times Y term on the right to the left. And I already have one term of Y on the left, so I have 1 plus GC Y equaling GC R. Is that clear? And now I will go ahead and put in the arguments. I'm going to solve for Y of Z. Y of Z, I can just divide both sides by 1 plus GC. where I now have G of Z, C of Z, over 1 plus G of Z, C of Z, times R of Z. And this is our transfer function between the reference input R and the output Y in terms of our plant G and our controller C. Questions on that? Now, and this is now a different cheer, isn't it? This is a different cheer. Last time I think I said we had G in the forward path and we had H in the feedback path, and we said give me a G, give me an H, give me a G over 1 plus G. That's not what we have here, is it? No. Now I have a G in the forward path, a C in the forward path. In our block diagram, I have a G, I have a C, and I don't have an H. My H is 1 in the feedback path. So now if I give you a G and I give you a C, you can give me the closed loop transfer function, which is our cheer. GC, which is the product of the forward path, over 1 plus that product. GC over 1 plus GC. That's our closed loop transfer function. What we want to do now is, with the Ragazzini approach, we now say, oh, here's what I want for T sub C of Z. This is what I have for the plant G of Z. What do I need C of Z to be in order to give me T sub C of Z? That's what we're doing. We formulate the desired transfer function. We start with a T sub C of Z. We have a G of Z. Now we have to solve for C of Z. And we know they are connected by this equation, or this expression. Whoa. Or if T sub C of Z is G of Z, C of Z, over 1 plus G of Z, C of Z, what we need to do then is solve for the controller. Because in this Ragazzini approach, we find a desired transfer function. We know what the plant is. We now want to determine what is our controller, C of Z, such that when it's combined this way with our plant, we'll produce T sub C of Z. Now we just need to basically back out C of Z from this formula. That's where our controller design formula is coming from. Let's do that. So now, based on this relationship, what if I cross-multiply or clear the fraction? I'm multiplying both sides by the denominator, which is 1 plus GC. If I do that, I now have 1 plus GC times the left side, which is T sub C, all equal to GC. I just came from a lecture about the grand challenges, so now all I can see when I see GC is the grand challenge. But GC in this class is the plant, and this is the GC state, isn't it? It's the Grand Canyon state. GC can stand for a lot of things, can't it? Grand Central Station, maybe. But anyway, all right, let's get back to class. So now we have, is everyone comfortable with this equation from the relationship between T, G, and C? Now what we want to do is try to isolate C. So we have T sub C, or distributing T sub C through on the left, we have T sub C plus GC T sub C is equal to GC. I'm doing this in a lot of steps. Then I can try to combine my terms that involve c, so that I now have t sub c is equal to gc minus gc t sub c, or I can factor out a g on the left, and let me factor out the c on the right, so that I now have 1 minus t sub c, c. Hopefully I haven't done anything wrong algebraically. These are now scalar transfer functions, so I can pull those in and out on the left and or the right. And as I said, I'm now wanting to solve for, so now I have t sub c equal to g 1 minus t sub c, c. I can now solve that for the controller c sub z by dividing by g times the quantity 1 minus t sub c. And if I separate those out, I'm dividing by g sub c, and I have t sub c of z divided by 1 minus t sub c of z. This is now our direct controller design formula. And hopefully now you're comfortable with just using it. And what this formula is really saying is the controller would ideally like to simply cancel the transfer function of the original system. That's what it's doing by saying 1 over g of z. But we also know that we cannot cancel unstable poles or zeros, and that's why we have to impose these restrictions on t sub c of z. We need t sub c of z to contain the same unstable zero factors. We need 1 minus t sub c, the zeros of that, to cancel the poles of g of z, and then we are not going to be canceling unstable poles and zeros with our resulting controller c of z. Questions on that? So now we've looked at restriction 1, we've looked at the design formula. We're trying to get through all of these justifications for the different restrictions. And do I really need to cover restrictions 2 and restrictions 3? I just verbally did. Restriction 2, I hope you can see why, if we want c of z not to be canceling unstable poles and zeros, then we need to get rid of those factors that occur in 1 over g of z. And the way that we can do it is by imposing certain conditions on t sub c of z. R sub 2 deals with the zero factors that are outside the unit circle. Restriction 3 deals with the pole factors of our plant g of z that are outside the unit circle. And if we don't have those, then we're happy to cancel those with this formula. We don't have to impose those restrictions on t sub c or 1 minus t sub c of z. So we're done with restrictions 2 and 3 justification-wise. And what you can do is you can start to look at that relative to this design formula and see if that indeed does make sense. So let's now look at the last restriction, R4, which was dealing with steady state accuracy, or you might refer to that as the steady state accuracy constraint. In some cases, we may not impose any steady state accuracy constraints. Remember our first design? I injected a 1, and where did I end up? You remember from last time? We went below, didn't we? We went to where? -4? So there we weren't concerned so much with steady state accuracy, but we might be. So here, R4 is saying that steady state accuracy may impose additional constraints on our desired closed loop transfer function, T sub C of Z, as Z goes to 1. And if Z goes to 1, that's in the steady state, isn't it? That's at DC. That's where we might have reasons for imposing restriction 4. As an example, in our block diagram where we had unity output feedback, the E of Z was this difference between where we wanted to go, R, and where our output went, Y. E was the output of that leftmost summing junction, and that was R minus Y. But we can rewrite Y in terms of R. Y is just in terms of R isn't that how we define T sub C of Z, our desired closed loop transfer function? That's just T sub C R gives us Y. If E is now R minus T sub C R, we could also rewrite E as 1 minus T sub C of Z times R of Z. So here's a relationship in this unity output feedback configuration between the error signal and the reference signal and our desired closed loop transfer function, T sub C of Z. If we want zero error due to a constant input, if little r of n is constant, let's say it's a unit, let's say it's a step input, what is capital R of Z? What's the Z transform of a unit step? Remember? Is it that? So now if we apply a unit step, we want to know what's the error signal, or what's that impose on T sub C of Z. If we want zero error due to a unit step, then we can use R, capital R of Z equaling Z over Z minus 1 and the final value theorem to yield the time domain error, E at infinity, is now equal to the limit as, let's say, the time index n marches off to infinity of little n, but by the final value theorem, that's now the limit as Z goes where? You remember? So the time goes to infinity, the n goes to, I'm sorry, Z goes to its DC location, which is z going to 1, and now we have z minus 1 times the z transform of little e of n. But we have an expression for capital E of z in terms of r and 1 minus t sub c of z from before. So that now this e of infinity is equal to the limit as z goes to 1 of z minus 1. E of z was 1 minus t sub c of z times r of z, which was z over z minus 1. And we can start canceling some common pieces. That z minus 1 cancels that z minus 1. And if we want this to equal 0, as z goes to 1, what does that imply for capital T sub c of z? Or this is now another way of saying that is we're now saying the limit as z goes to 1 of T sub c of z, if I push that on the other side, is equal to 1. Or we are saying that T sub c of z at z equal 1 is equal to 1. So this now is saying that the DC gain of our desired closed loop transfer function obeys that relationship. If we wanted 0 error due to a constant input. Now we could carry that even further if somebody says, oh, I already know that that's going to happen. I want to impose a error on a ramp input. So now we're going sort of to the next possible reference input. I won't derive it, but if you wanted to look at the next step up in terms of satisfying steady state accuracy specifications, there's a velocity error formula. And this one now says that you take minus the sample period times the derivative of your desired closed loop transfer function with respect to z, and set that equal to 1 over k sub b. When you already have ensured that the desired closed loop transfer function at z equal to 1 equals 1. So if you need to go a few steps beyond where you are at presently, in terms of, oh, I want to have something beyond just having a 0 error due to a constant, I now want an error due to a ramp of, let's say, 1 over, or where k sub b is going to shrink our error due to a unit ramp by the ratio or the power or the size of k sub b. The error due to a ramp is 1 over k sub b. So if we want to shrink that, we pick an appropriate k sub b and figure out what the parameters, the adjustable parameters in T sub c of z, we would have to impose some more, need to be, in order to satisfy this relation. Those are now the justification of restriction 1, restriction 2, restriction 3, and restriction 4 of the Ragazzini design. You now have a way of designing a controller. It may not be the best controller, but you can now create a controller for a given plant. What we now want to do is look at some additional controller design techniques or strategies. What are some better ways to control the system? That's what we want to talk about next. Yes? So now the question was, the Ragazzini approach that we have worked through is assuming this formula for the controller design formula is assuming that we have unity output feedback. But you could rederive this with a non-unity gain or transfer function in this feedback path. It's just that that would mess or make the formulas a little bit more complicated, and that doesn't really change the thought process or the strategy. But yes, it could be done, but in fact, we have restricted this design to be utilized when we have a 1 in that feedback path. And that's what we'll assume if we are starting to do the Ragazzini design. We're assuming that controller structure, or that closed loop control structure. Does that answer your question? Any other questions? On to B. Oh, what? Wow, okay. We have some more novels to read, don't we? I was up late last night, getting ready for this, maybe. I don't know. Oh, this is kind of weird, huh? Let's now talk about PID. Or if you've taken an earlier controls class, you know that you don't say PID. It's a PID controller. It's an acronym. It stands for proportional, that's the P, integral, the I, and the D is derivative. In a block diagram, when you hear a PID controller, you might be envisioning this block diagram configuration. You have your system, your plant, G of Z, and now really you have 3 different pieces or parts to a controller. You have the air signal, which is this R minus Y, but now you do 3 different things with that air. One, you simply scale it proportionally. The other, the middle path, you integrate that air and then gain that up and add that in to influence the input to your plant. The bottom parallel path of this PID controller is saying, take the derivative of the air signal and scale that. And what you want to be starting to do now is develop a little bit of an insight or feel for what that means. Proportional, integral, and derivative control. And that's what I hope to convey with this story that I'm going to tell you next. Yes? So now the question was, is there a timing difference in generating this air signal? Now, what we're assuming is that if I start clapping, that things are happening at a clap. Meaning, if I clap, not too fast so that we understand, but if I'm clapping, let's say that's n equals 0. Then we have r of 0 and we have y of 0 at that same instant. And we're assuming that that instantly, that y at that time instant is available at that summing junction. So we have r of 0, y of 0. That creates e of 0. That's our air at time 0. Then if there's some delay in this proportional and plant, which there will be, because it's dynamic, then that will propagate through and influence the output in the future. But we are now generating the air signal now based on the reference signal now and the output now. And all of that will start singing together, but we want it to sing beautifully and produce what? desirable closed-loop behavior. We want to figure out how do we adjust the gains of these three pieces, the proportional gain, the integral gain, and the derivative gain, such that we have a well-behaved system response. And what we want to do now is try to understand what those different pieces might look like. That was not my clap. That was n equals 0. Okay, so P, I, and D. We have, and I'm illustrating this with continuous time because it's easier to think about when I talk about integrating and differentiating in an analog setting. But we can translate these operations into their discrete equivalent based on what we've done for exam number 2, for example. But if we now have a proportional gain or a proportional controller, then we are taking the air signal, scaling it by a factor k sub p, and injecting that into the system. So now what you could do is, as I'm talking about this, you could virtually erase the integral and the derivative piece and say, oh, what would happen if I just had a proportional controller? It would take the air signal at the present time, E of t, and scale it and inject that into the plant. That's the use of p at the present time. That's the input to the system at the present time. If I wanted to understand the integral piece of this PID controller, now what I'm doing is I'm integrating that air from previous airs, and it's just growing possibly, unless it goes positive and negative, which it could. But now I'm worried about the integral of the air, and then I'm scaling that with this gain constant k sub I and injecting that at the present time into my plant. And I hope you can see that this integral involves past or previous air signals, because you're integrating what happened before time little t. And the derivative term, so we now have p proportional, that's like dealing instantly with the present air. The integral piece is worrying about the air that's happened in the past. It's integrating all of that history. And the derivative piece, what's the derivative piece? That sort of is telling you where you're going. Where are you anticipating to go? So it's now differentiating the air and responding to the derivative of the air signal, so that you now are worrying more about future behavior relative to your air signal. The derivative term works with the anticipated or future air movement. So PID, a three-term controller, works with present, past, and future type information. And that should give us a lot of flexibility in adjusting the behavior of our controlled system. That's the idea. And here's another way of maybe looking at that. Suppose that our air signal is shrinking. That's what we would prefer, right? We would like the output to be getting closer to the reference input, so we would like our air signal to be shrinking. But these different pieces, the proportional, integral, and derivative piece, are working relative to the present or the now. The now piece is the proportional piece. So if you want to make your past air more significant, then you might enhance the integral gain in your PID control, where it's now emphasizing past air information. If you want to emphasize the present air, then you might, relatively speaking, increase the proportional gain. Or if you want to make your system more sort of anticipatory in terms of how it behaves, then you might be adjusting the derivative gain. And we'll see that we can adjust those three pieces to move poles and zeros around in our controller to maybe change the dynamic behavior of our closed-loop system. But in a sort of intuitive thinking sense, this is a way to keep track of your error signal and how it's modified or manipulated with a PID control. That was 3 pieces. Let's just worry about our wild card, our one piece today. I just have to pull somebody out of the audience, right? Come on down, so that you can now, the price is right, and we'll perform on stage. I don't know, somebody asked if we were going to dance today, but we'll do that after class, maybe. So if you're home listening to this, you can get out your records and start dancing, or your orchestra, whatever. Now, we are going to concentrate on one of those pieces, the proportional piece now, to gain insight. We can get quite a bit of information out of looking at one of these controllers. Here we're saying our controller is just K. It's going to immediately, or it's just going to operate on the error signal at the present time. Let's just look at what happens, or what can we do in a closed-loop scenario with just proportional gain, or a proportional control. We can use our cheer, correct? That was CG over 1 plus CG, but now C is K. So now we have our closed-loop transfer function is KG over 1 plus KG. And G, in general, is a ratio of polynomials. So here in T sub C of Z, in this formula, we have a ratio of ratios, right? The numerator has a numerator and denominator, and the denominator has a numerator and denominator, because it contains G of Z. But the dynamics of this closed-loop system are influenced by the denominator piece of T sub C of Z, and the denominator piece is governed by 1 plus KG of Z in that expression. So we are interested in manipulating 1 plus KG of Z, or the zeros of that, by adjusting K, the proportional gain. We want to know, how can the zeros of this expression be influenced by manipulating K? So we adjust K, we then set that equal to 0 and see where the zeros of that formula or that expression end up. Let's look at an example. So now, again, you can pull out your paper, not your cell phone, and you can start following along. Let's now assume that we have a plant, G of Z, that is equal to 1 over Z minus 2. Do you like that plant? Or what can you tell me about that plant? It's unstable, isn't it? So if you excited this system, if you hit this system with an input, it's going to go unbounded. Now do you know the structure of your response? What's the structure of your time domain response due to this system? You find your roots of your denominator, you find your poles, you look at their R's. In this case, where is your R? It's a 2, and you're now raising that to higher and higher powers of n. It's just going to expand, isn't it? So let's see what we can do with a constant output feedback. T sub C of Z is our cheer, CG over 1 plus CG, where C is K. We're just assuming it's a simple proportional controller. This now becomes K over Z minus 2 over 1 plus K over Z minus 2. So now my Z's have a line in the middle. The 2 looks kind of like a Z, but it doesn't have a line in it. Zebras have lines, so that's good. All right. So now we have K over Z minus 2 over 1 plus K over Z minus 2. Let's get that as just a ratio. so that we now can say, let's put everything over z minus 2 and cancel that z minus 2. And we now have k over z minus 2 plus k. That's our closed loop transfer function. And we can adjust that by adjusting k, the proportional gain term. What are the closed loop dynamics? What do I mean by that? Or what's governing the closed loop dynamics? Or am I using words that you're not comfortable with? What are my closed loop dynamics in this capital T sub C of Z? What influences the dynamic behavior of this system? What do I mean by dynamic behavior? Well, the dynamic behavior are these structures that you've talked about already. If I said, what's influencing the structure of this transfer function, what would you be looking for? The poles, right? Can you find the poles of this system? They're buried in that denominator expression, aren't they? They're the values of z that cause that to vanish. Those are the poles. So the closed loop dynamics are governed by 1 plus k g of z, which is right there, and that now is giving rise to that denominator expression. Or you could say, if the dynamics are governed by the denominator, which is 1 plus kg of z, we could also say that that's now the roots of 1 plus k g of z equaling 0. We're really just setting this equal to 0. And if we simplify that, we want to know, when does that vanish? Well, that vanishes when the numerator of that mess vanishes. And the numerator of that mess is z minus 2 plus k. Or the numerator equal to 0, and that, let me just go ahead and say, the numerator of that was z minus 2 plus k, and we're interested when that's 0, and we actually refer to this. I did write numerator. Numerator of 1 plus kg of z, which is, this is 1 plus kg of z, and I'm interested in the numerator of that expression, which ends up being z minus 2 plus k, and I'm setting that equal to 0. That governs the dynamics of this system. But it's all coming from 1 plus k g of z. And we call this right here the closed loop polynomial, or the characteristic polynomial. And what we want to do now is look at what happens when we have freedom to manipulate this proportional control, this k value. That's what we're putting into the system. Can we now adjust k to move the dynamics in a more appropriate way, or make those more appropriate? We want to now adjust k to locate the closed loop poles this case, it's just a pole, so we'll just say the closed loop pole at an acceptable location. CL is that CL there. Closed loop polynomial. All right. So now, what are we looking at? We want this closed loop polynomial. We're setting it equal to 0, and we want to know what values of z cause that to vanish. So we can solve that for z, or we now have z is equal to 2 minus k. Are we okay with that? We can adjust k to give us a z value that maybe we like. Can we do that? And we can actually look at that in the z plane to maybe give us a little bit more insight. If k was equal to 0, if k was equal to 0, where would our pole be? Where would the value of z be if k is equal to 0? Pardon? I don't have my glasses on, so I can't hear you. 2. So now we started with our open loop system. If k is 0, that's our open loop system. It was unstable. We didn't like that pole, but this is now our open loop pole. But do you see what's going to happen as we apply bigger and bigger values of k? If we increase k from 0, what's going to happen to the value of z? Suppose I plug k equal to 1 into that expression. That's our dynamics. That's governing our dynamics. What happens when I plug in k equal to 1/2? You see that I'm now right here if k is 1/2. If k is 1, I'm right there. If k is 2, I'm right there. If k is 3, I'm right here. Do you see that as I adjust k, I can place my dynamics anywhere to the left of that initial open loop pole location? Meaning, as k increases from 0 to infinity, this red line gives me the locus of potential closed loop poles. And if you have some control background, you're going, that's a root locus. That's the root locus diagram. But we'll expand on that a little bit more. But what can we see? What's one possibility? We're just trying to find some acceptable values for k. One possibility. I need to check my English. One possibility. Z minus 2 plus k. This is our closed loop polynomial. What if we wanted a pole at 1/2? Then we could set that equal to our desired polynomial. Let's say this is our desired polynomial. And do you see that that would give us a way to find what k needs to be? If we equate the coefficients on the left-hand side and the right-hand side, I hope you can see that if we compared the constant coefficients, z to the 0 coefficients, we have minus 2 plus k equaling minus 1/2. Or k is equal to minus 1/2 plus 2, or 3/2. And if we now cranked up the gain from 0 up to 3/2, we would end up with a desired closed-loop transfer function having a denominator of z minus 1/2, and the numerator was k. And what do we know about the closed-loop system in terms of behavior? Is it stable or unstable? Where's my closed-loop pole? It's of 1/2. I've now pushed that from outside the unit circle, inside the unit circle. I've stabilized my system with a proportional controller, and now maybe I like the way that system is behaving. That was done with a basic proportional controller. So my closed-loop system is stable, and in order for this class to remain stable, we'll have to stop at that point, and we'll pick up somewhere with more parts of this PID controller the next